Hello everyone, December 17th. Alright, first things first, I finally solved this problem. My god. I finally did it. Yeah, I'm gonna go back to this again today and then kind of just go through all the logic and finally can be done with it. But we need to put this in our nightmare list. This one is tough for me. Very, very tough. And I don't want to do too much today because I did a lot of talking today and my throat is actually hurting. So we're just gonna do this and do the recap of that problem and then we call it. All right, what do we have for today? Daily temperatures. Given an array, represent the temperature, return an array answer such that answer I is the number of days you have to wait after the ith day to get a warmer temperature. If there's no future day for which there is possible, return 0. So we want to say answer I is the number of days you have to wait to get a warmer. So 73, we have to wait 1 day. 74, 1 day. 75, 1, 2, 3, 4 days. 69, 1 day. No, 71, 2 days. 69, 1 day. 72, 1 day. 73, 76, no days. Okay. So we just want to know the first value that's bigger than me and where it is. So we probably can go from right to left. So the first one be 0. And then for this one, if I know the maximum so far, so this will be 0. And then this, so maximum will say, maximum will be here. We know its position. Man, but what we want is not a maximum. We want a value that's just bigger than it. So this one will be 1, right? So we know it's bigger than this. And this is bigger, so it'll be 1. Okay, so about this one. So for this one, I know this is smaller, but the one bigger than that is going to be 1, so it'll be here, right? And I know its position, and then this one, so it's going to be this minus this, so that will be 2. Coming here, so this bigger than 1 has to go 2, so we go here. But bigger than that is going to be here, so that will be 4. And 74 will be that. 73 will be that. Yep, I think this one will work. So it's a DP for sure. Man, I can feel my throat, so I'm trying to talk really softly. We probably can. Nah, I don't like it. I like just to do it like this. Okay. And then we say for I in range, land temperatures minus 2. Why minus 2, you ask? Because the last one has to be 0, right? So for each one, we're gonna go to the right. Not really go to the right, we just want to get the index, right? So what we do is we say j is equal to I plus 1. Okay, so while temperature j, if it's smaller, would it be equal to? Warmer, so have to be, if it's smaller or equal to temperature is I, then we say j plus equal to j plus equal to what? J will be plus equal to res j. So we know we get the new one, and then we do this, get a new one. Eventually, we'll find something that's out, or while j is smaller than land. Oh, might as well do this. Temperatures this will be n, this will be n, right? When you get out, and we say res I shall equal to plus equal to res j. No. Res I, not plus equal to, equal to if I'm something, so we can say j minus I, right? Yeah, j minus I. But what if j is bigger? Say if j is smaller than n, else 0. And now return res. Alright, let's try. Check the runtime might not be. The runtime might not be friendly though. Oopsie doozy. Why is that? Because I start from here, so I is actually equals this. So if it's going to be 0, j plus, so if if it's gonna be 0, which means 0 days, so yeah, so if res j is 0, which means that this day we have nothing is smaller. So temporary j is smaller than that. Okay, then we need to find the next one. But if res j is 0, then which means there's nothing smaller than that. Yes. So if it's 0, then we jump out. So when we jump out, it depends on res j actually. Yeah, because eventually we will go to the last one. If the last one is bigger then yeah, I don't think this one is necessary. Because the first one, right, it will be 0, so we will be jump out. Right, so we can just say res j, right? If res j is not 0, right? If res j is not 0, that means there's something, right? There's something that I can, and then you always stop at something, right? If you stop at something, it's because either temporary j is hold on. I like to say if temporary I is larger than temporary j, larger or equal to. Yeah, if I am larger or equal to, then I need to find the next one, right? and I have larger equal to, I need to find the next one until at a point I'm still larger or equal to, but rest j becomes 0. So we come out, right? So I want to check if rest j is equal to 0, then it's just 0, which means I cannot find one. Otherwise, I'm going to be this. Oh, that's not right. That's not right. Oh, no, that's not right. That's not right. Just start to repeat this. If this is larger than, then j, because j we're pointing here, right? J when we add to it, and then come back again, then we should say if rest j is 0, then we shall break, right? So for the other ones, how about this, right? This comes in here. This is larger or equal to, say if not rest j, then we shall break. Well, that's the same. I is smaller than that, right? And oh, this one is still 0. And how do I handle the end? Well, what we can do is this is larger than, then I do this. But after I do this, if j doesn't change, yeah, we can come out, but the thing is here, this one needs to change. We can do that. We can say if temperature I is indeed smaller than temperature j, otherwise it will be 0. There we go. That's more likely. That's more likely. Well, we can run test case as well. Oh, I like this test case. Easy to do. How many? Still 100. 30 to 100. Ah, that's Fahrenheit. Wait, so 100, not 199. Seem to be right. My suspicion is we have a new test case. 47. 48. Got one more test case. Okay, this one is the previous solution. Let's see. Find range J, I have a temp. That's exactly the same. Ah, this is already using O1 extra. I think this is already using the optimized one, which means the original one probably has multiple arrays. Yep, I have multiple arrays. So yeah, this is the optimal, at least from my previous experience. Well, it took a little bit longer than I want. DP. For each temperature, find, check its next temperature. If it is higher, we're done. If not, jump to the temperature that is higher than the next temperature, rinse and repeat. This is what we can say, amortized ON, unless, no, there's no unless. No unless, amortized ON. There's no worst situation. It might be, but it's okay. All right, so we're done with this. Now back to this. All right, the solution was good, right? The solution that I checked yesterday was good. So basically what it says is so there are two types of indices. One type is the good index, which means nums1, nums2 are different. The other is a bad index, which means num1 is the same as num2. So what we do is we put all the bad indices to position 0. Because the ideal is if we use the position 0 as the transitional space, right? If we move something to 0, right, we do swap with 0, and then we do swap with the other one, what we achieve is the same as swap those two. Like if we want to swap 1 and 2, but instead of swapping 1 and 2 directly, I do 1 and 0, right? And then I do 2 and 0. Then this swapping results is the same as swapping 1 and 2, which is equivalent to taking 1 and 2 to the 0 position and then redistribute 1 and 2. So that's the basic idea of redistribution. So what we do is we will go through everything, find the bad indices, and put them into the 0 position. But we don't really put them into the 0 position. We simply, using a counter, we count them, right? Count the occurrences of them. And then when we redistribute, the total cost is just the sum of the indices, right? This is we get in the total cost, the sum of indices. And in the meantime, we also record all the good index that we can have. All right, so these are the indices are good, which we will use later on. And after we get all of them, right, we get all the bad indices. Now this is a very important one. We need to find the most common value in the bad index. Because when we take them away, okay, we take the bad indices away from nums1. On nums2 in the same position, we have the exact same numbers as the one we take away, right? For example, in this case, we have 2, 2, and 3. These are the bad, so we take them away from nums 1, but at the same position on nums 2, we have 2 to 3, so we have the same thing. And then we want to redistribute 2 to 3 into those positions. Then we have an issue, right? Because we have more than half of them are 2s. So if we imagine, if we have 2 to 3, these are bad. So we have, the most common is 2. We have 2 2s, right? So in order for there to be no overlap when we do the overlap, so we need to have these 2s not overlapping with the 2s in the current available positions, right? So we need at least 2 times 2 equals 4 open spots. But now we only have 2 to 3, so we have only 3 spots. So that's not possible. This is the pigeonhole problem, right? So we need to at least have 4, but we only have 3. So we need to increase the number of open spaces. And that's when the remaining indices come into play, because we only want to take the smallest index. So those are good indices, but we want to take the smallest to open up new space. So that's why we have this is the available spaces left, right? After we take away all the bad indices, and this is the most common value, the most common number among the bad indices. And then we will go through, right? We'll go through everything. We'll go through all the available indices. We want to check. What do we check? If we double it, right? Because that's what will happen. We need to have the available spots be at least double of the most common value in the bad indices. So we double it, right? If we double is larger than the available indices, that means no good. We need to take away the good index in order to build, to expand, right? To expand our available indices. And when we take the good index, we have to make sure we do not take the same value as k, because if we take it, then we will increase C1k by 1, or increase this by 1, and but we do, and then so the overall, like this one will not change, right? This one will not change. So if we take the same value as the most common one, we will never make the situation better. It's actually making it worse, because if we add 1 to it, so this one double, so every one of the k we take in order to expand available positions, we are expanding the requirement by 2. So this actually makes things worse. So we have to skip both on num1 and num2 if it matches. So we take the one that does not match k, and we take that, we again increment on the result, and then we increase the available. And see, we only increase this, we do not increase C1k. So at a certain point, right, at a certain point, we will either satisfy the requirements, right, and then we will break out, or we don't satisfy, which means we take away everything. We take away all the available spaces, but we can still not satisfy this criteria. That's what we do at the end. If we still cannot satisfy, we'll return -1. If we can, we'll return res. And again, the reason we can return res is because everyone will go to the 0 first, right, and then redistribute. So we just need to add all the indices together. That will be the minimum cost. So that's the overall. And it's tough. It's very tough. I did notice that if you go to 0, that will be actually free. You got a free ticket, right? I noticed that, but I was struggling because I was trying to see if I go to 0 and I need to, what was my initial struggle? The initial struggle is I know I need to go to 0, but then I'm struggling to find out where I shall go afterwards. What I did not realize is this redistribution. You just redistribute them, and that's the thing I didn't realize. And then I read the hint, which I know that we need to pair. So then my idea goes to pairing. I find all of the bad indices and I try to find a mechanism to pair them. And I have a lot of tries to like design. We need to pair the small with the big, but then I realize if I do that, then sometimes we need to pair the equal with equal. So there are so many different situations that you cannot simply cover with pairing. So that's when we give up. And then we see the results. And then we realize that this whole problem can be simplified by this way of thinking. We do use 0, right? But then the ideal is when we get a 0, we don't really care about the distribution. So like the previous method I had, I always try to figure out the best way to do the distribution, like the detail, like which one pair with which. But we don't have to, because the redistribution, no matter how you redistribute, the total cost is the same. It's the same. We redistribute all the indices, it's the same. So the effort is not at how to redistribute, but at which good indices need to be sacrificed in order for the most frequent bad indices to be properly distributed. So that's the most effort that we're doing. And that is also something I didn't realize. That's why it took so long. I think overall, I mean, you see only 2 days, but if you take a look at the actual time I spent, it's way longer. I'd say maybe 4 days to get this done. Because nowadays I don't really submit to find the error cases. I usually I'll build a case myself. So you don't see a lot of submission here, but overall it took a long time. Yeah, it took a long time. All right. That shall be it. Yeah, we have 12-13 here, right? I remember 12-13, that day we probably did 2 of them, and 14. Yeah, I think it's starting from 14 to now, 4 days. It took 4 days. That's a really long time. But anyway, we're done with this finally, and that's it. I don't want to do another one today. We can open. I mean, we have contest today, but I skip it. We can open the problem. These will be for tomorrow. Yeah, I still don't have Ghana to do the actual contest. All right, I'll see you guys tomorrow.